The belief that Vigenere was unsolvable revolved around the possible combinations of key letters in a brute force attack on the key. A keyword 6 letters long represents 26 times 26 times 26 times 26 times 26 times 26 combinations, or 309 million possible keys for one message. Keep in mind, though, that if you managed to get 3 letters right, you'd be able to slowly piece together the rest of the key based on the readable text you could tease out of the message. So the total number of combinations isn't that insurmountable. But if one approach doesn't work, there are always others available to us that will. We'll explore 3 methods for manually attacking Vigenere ciphers. We have Probable Word, period testing, and the Kasiski Test. First, we'll start with Probable Word. The weakness exploited here is that the Visionaire family of ciphers are reciprocal. That is, if you have the plain text and the key, you can create the cipher text. And if you have the plain text and the cipher text, you can extract the key. Let's see how this works using our practice cipher. V1, Visionaire. A matter of taste. Hint word, whiskey. There are a couple ways to do this. One is to write out the cipher in lines, with each line shifted 1 letter to the left without wrapping. Then Caesar shift each line with 1 letter of the probable word at a time. Let's use the Visionaire slide for this. You may want to do this in blocks of 5, just in case you extract the key towards the beginning of the message. Write out the hint word in a column. Next to W, write out the entire cipher. Next to H, write out the cipher shifted 1 letter to the left. Next to I, write the cipher again shifted 1 letter to the left. And continue down to Y. For the first line, set the slide to A equal W. Look for O on the lower slide and write down S from the upper slide. H, write down L. Y, write down C. I'll continue for a total of 10 letters. Set the slide to A equal H. Starting with H from the cipher text on line 2, look for H on the lower slide and write down A from the upper slide. Y, write down R. And continue. And just Caesar shift each group of 10 letters down to line 7. A equal I, A equal S, A equal K, A equal E, A equal Y. It may be a bit difficult to pick out right away, but our key shows up in column 8. We can see that from the top line, we have ULT, and lines 6 and 7 repeat UL. Writing out our cycle, ULT, VAULT. We get the keyword vault. Alternatively, we can slide the probable word across our message and decrypt the letters under it as a block to see if any readable text pops out. First position, no. Second, no. Third, no. Fourth, no. Fifth, sixth, seventh, eighth, stop here. Back, fill in the key. Recognizing vault as an English word, we decipher the message as described in episode 12. The best whiskey is the one you like, the way you like it. And we're done. I hope that at this point it's pretty clear that the Visionaire family of ciphers is just groups of Caesar shifts. The letters in each group are determined by the length of the keyword, or the period of the cipher. Therefore, if we can determine the period, we can solve each group as a Caesar shift graphically to recover each key letter. There are two ways to do this, as mentioned earlier. We'll start with period testing. This simply means that we write the cipher in columns or rows, whichever you prefer, as if we know what the period is. The ACA guidelines state that the cipher length is period times 10 to 15. Using practice cipher V3, Beaufort, shell gives the bird, our length is 110. Our period should be between 7 and 11. Write out the message in columns 7 lines deep. Picking one of the longer lines, we do a frequency count. Then we graph that and compare it to the normal English letter distribution. Keep in mind that this is a Beaufort cipher, so we need the x-axis of our cipher graphs to read Z through A. Does this distribution look kind of right? Yes or no? I guess I'd call this a broken comb pattern. We've got one each of entirely too many different letters. So no, it doesn't look right. Try again with period 8. Oddly flat with two spikes close together. They could be R and S, or S and T, but the valleys aren't really spaced right. Let's keep going. Try again with period 9. Okay, this looks a lot more like our normal distribution. The problem is that we only have 13 letters in the line, which isn't a lot. Let's shift the graph to see if we can align it with our normal distribution. At D, it looks like it matches up well enough. So we can assume that we have the right period. We could now continue on to solve for the full key. Before we do that though, let's also look at the third method, the Kasiski test. The idea here is that with a long enough message, certain combinations of letters, pairs, or triplets will be enciphered with the same letters of the key because they match up with the cipher period. For example, using a key of key and the message 33 trees, we get the following cipher. Yes, this is contrived, but it's good enough for jazz. We have the diagram, or letter pair, DL, appearing at positions 1 and 7, counting to the first letter of each pair. Subtracting the first diagram position from the second, 7 minus 1, we get 6. The usable factors in 6 are 2, 3, and 6. Any one of these could be the correct period, or the repetition of DL could just be a coincidence. If possible, we'd like to see more than one repeated digram, or ideally, trigram. And the farther apart the n-grams are, the more likely that the repeats are not just a simple coincidence. Returning to V3. In this message, we have the trigram letter triplet, DER, appearing at positions 55 and 73. 73 minus 55 is 18. This gives us the usable factors 3, 6, 9, and 18. Our guidelines suggest something between 7 and 11, so we can assume that our period for this cipher really is 9, as given in the earlier period check. Okay, we have 2 steps. Get the period, then solve for the key. We can use the manual graphic period check or the Kasiski test to determine the period. Then solving the cipher manually from this point is the same either way. Write out the cipher in columns or rows, your choice, in period depth. As mentioned before, with only 10 to 15 letters per block, it's a lot more challenging to determine the shifts for each block. It gets especially harder if the text has a lot of normally low-frequency letters, and few E's, T's, and A's. One thing that can work for us is if the keyword is in our dictionary, and we can try solving for that as we go. Otherwise, we may have to print out as much of the plain text as we can get, and slowly tease out individual words one at a time. Let's start with the first block. Looking at the letter groups with period 9, we've already solved the shift of group 1. In our period check step, we verified that the period is 9 when we found that group 1 was shifted by D. Go to group 2. This is really unbalanced, with 6 E's out of 13 letters. Skip for now. Try group 3. Shifting the graph so that A equals U. We kind of get matches on A, E, I, S, and T. We can now ask, is there a real 9-letter English word that starts with D something U? Granted, our key could be someone's name, or a short multi-word expression. But let's use an online word finder. I have the link for one pinned in the description below. The answer is yes. There are 29 matches. Let's keep going. Group 4. Not great. Skip. Group 5. Another broken comb. But what happens when we try lining up the valleys with what we expect to be really low-frequency letters like J, X, and Z? A equals S looks promising. We have valleys in the right places, and a string of spikes from R to U. Checking for words matching a D something U something S pattern, we get drugstore and drumstick. The title of the crypt is Shell Gives the Bird. Drumstick fits in thematically, and it doesn't hurt to just plug in the key at this point and decipher the crypt, as described in the episode 12 video for Beaufort. Thanksgiving dinner's sad and thankless. Christmas dinner's dark and blue, when you stop and try to see it from the turkey's point of view. I'll let you examine the other group frequency distributions and see how they fit the Caesar shifts for each key letter on your own. Recap. There are 2 primary ways to solve the Visionaire family of ciphers. 1. Place the hint or probable word. 2. Determine the period of the cipher. Then find the Caesar shifts for enough of the individual letter groups to allow for solving for the keyword. We can place the hint either by Caesar shifting the entire cipher, one key letter at a time, and look for word fragments that pop out. Or we can slide the hint across the entire cipher, one position at a time. We can determine the period by either writing out the cipher in columns or rows and checking one of the groups graphically for whether it fits the normal English distribution. Or we can use the Kasiski test and look for the distances between letter pairs or triplets that appear 2 or more times each. It's that easy. And we're done with part 1. See you in part 2. Got questions, comments, or suggestions? Leave them in the comments below. Enjoyed this video? Then I encourage you to hit the like button and subscribe to this channel. If you want to show further support, you can join us over at the Black Chamber Patreon page, where you can get access to more how-to videos and PDFs on solving the cipher types covered here, additional crypts to solve, and more. Links pinned in the comments below. See you at the next drop point.